Friends, welcome to Acharya Gurukulam. Today's topic is design horizontal base shear force, a solved example. In this video, I am going to explain the design horizontal base shear force as per IS 1893-2023 draft code and IS 1893-2016 code. A architectural plan of G plus 3 building is considered for the calculation purpose, whose length is 11.7 meters and width is 8.9 meters. And the specifications are as follows. Grade of concrete is M20, slab thickness 0.12 meters, wall thickness 0.23 meters, floor finish 1 kilonewton per meter square. Size of beams and columns are taken as 0.23 by 0.3 meters. The elevation and the beam column positioning are given in this slide. The height of each story is considered as 3 meters, and the bay width is as follows: 3.8 meters, 4.3 meters, and 3.3 meters. We will see the calculation part as per IS 1893-2023 draft code. In this analysis, we consider part 1 and part 2 codes for the calculations. Initially, we'll calculate the approximate fundamental translational natural period of oscillation in both x direction as well as y direction. As per IS 1893-2023 draft code, the fundamental translational natural period of oscillation is categorized into three categories. First one, bare moment resisting frame buildings without masonry infill walls. Second, RC structural walls. Third, all other buildings. In this analysis, I consider the TA, that is a fundamental translational natural period equation. TA is equal to 0.09 h divided by root d. Here, h is considered as the total height of the building, which is 12 meters, and d is the width in along x direction, that is 11.4 meters. From this calculation, that TA is obtained 0.32 seconds in x direction. Similarly, in y direction, the width d value is considered as 8.6 meters, and the TA value is 0.36 seconds along y direction. Next step is the importance factor. The importance factor I for building as per IS 1893-2023 draft code is considered categorized as follows. One, for normal buildings, important structures, critical buildings, special structures, and nuclear power plants. Because our case is for normal structures, and the design return period is 475 years we consider, and for building set 1, the importance factor from the code I is taken as 1. The next step is elastic force reduction factor R. The elastic force reduction factor R for special moment resisting frame buildings is taken as 5. Earthquake zone factor. Earthquake zone factor in the earlier version of the code, the earthquake zone factor is considered based on the deterministic approach, and in the current version of IS 1893-2023 draft code, it is considered as a probabilistic approach. Now you can see here a tabular column with zones, earthquake zones, zone 2, 3, 4, 5, and 6 with various return periods starting from 73 years to 9,975 years. For normal structures, the return periods for building set 1, for strength design, the return period is 475 years. For serviceability check, the return period is 73 years. So here in this IS 1893-2023 draft code, it considers both strength design as well as serviceability check. So significant revision has been taken place in the latest coming version of IS 1893. Assume that the structure is located in zone 2. For strength design, the return period 475 years, the zone factor is considered as 0.075. And for 73 years return period, the zone factor Z is considered as 0.0375. Now the values are written here. For 475 years, the zone factor Z for strength design 0.075. For serviceability check, the value is 0.0375. Next, normalized horizontal pseudospectral acceleration, that is ANH, for 5% of damping. The plot is drawn between a natural period as well as a design horizontal elastic pseudospectral acceleration. In this analysis, we consider different soil layers whose thicknesses are 1 meters, 1.5 meters, and 2 meters. And the corresponding corrected SPT values are 28, 32, and 35 values. Assume that the soil type is cohesive soils. So based on the information given in the table, we need to calculate the shear wave velocity at three layers. Layer at 1 meter, at 1.5 meter, and 2 meters. So the equation is used for cohesive soils as 100 into cube root of uh, corrected SPT value for cohesive soils. Whereas for cohesionless soils, the shear wave velocity V is equal to 80 into cube root of SPT value. Now, at 1 meter, the shear wave velocity value as 303.65 meter per second. At 1.5 meter, the value is 317.48 meter per second. At 2 meters, the value is 327.1 meter per second. After obtaining the shear wave velocity at different layers, then we need to calculate the Vs value, which is equal to sigma I is equal to 1 to number of layers, mm, hi divided by sigma I is equal to 1 to a number of layers, h divided by VSI. Now here the calculation is as follows. Hi means the layer thicknesses 1 plus 1.5 plus 2 divided by h1 divided by the corresponding shear wave velocity, that is 303.65 plus 1.5 divided by 317.48 plus 2 divided by 327.1. After simplification, we obtain the shear wave velocity is equal to 319.41 meter per second. Now, from the table given in the IS 1893 2023 draft code, the site class is D. The value is in between 180 to 360. So that's why the site class is D. Now, based on that site class D, the ANH 5% damping ratio value is taken as 2.5 for both x direction and y direction. The elastic maximum horizontal pseudospectral acceleration AH of t is calculated as AH of t is equal to Z multiply with importance factor multiply with ANH of t. So here you need to consider strength design and serviceability check both in x direction as well as y direction. And the AH of t in x direction for strength design is equal to Z, that is 0.075 multiply with importance factor 1, and ANH of t is equal to 2.5. So after simplification, AH of t in x direction and y direction, the value is 0.1875 for strength design. Similarly, for serviceability check, the value is 0.09375, both in x and y directions. Next step, the design horizontal acceleration coefficient AHD of t, which is calculated as AHD of t is equal to AH of t divided by R, where R is equal to response reduction factor. Here also you need to consider strength design and serviceability check both in x direction and y direction. In x direction, the value is taken as AHD of t is equal to 0.1875 divided by 5, where 5 is the response reduction factor, which comes 0.0375 both in x direction and y direction. Similarly, for serviceability check, the value is calculated as AHD of t is equal to 0.09375 divided by 5, which is equal to 0.01875. Next, the seismic weight of the structure W. The seismic weight of each floor shall be taken as its full dead load plus approximate amount of design imposed load specified in IS 875 Part 2, as specified in the table below. So this seismic weight shall be converted into seismic mass further. So if the imposed load value is considered as less than or equal to 3 kilonewton per meter square, then you need to consider only 25% of the imposed load. So if the value is more than 3 kilonewton per meter square, then you need to consider 50% of the imposed load. The seismic weight of the structure W is calculated as follows. The plan of the building is divided into three parts: slab 1, slab 2, and staircase. The calculation is as follows. The components are given in column 1: slab 1 load, slab 2 beam along x and y directions, column and external walls, at the end parapet wall. For slab 1, the length is 11.4 meters, width 6.6 meters, height or thickness is 0.12 meters, density 25 kilonewton per meter cube, and the number of slabs are slab 1 are 1. After simplifying, will arrive to 25.72 kilonewtons. Similarly, slab 2 load, length, width, thickness, density, and the number, then will arrive 45.6 kilonewtons. Similarly, beams along x direction and y direction are calculated as follows. Here, for the calculation of seismic weight for the column, the length or height is taken as 1.5. That is the half of the total height. So here the total height is 3 meters. So hence we'll consider half of the height, that is 1.5 meters, multiply with 0.23 and 0.3, that is the cross section, multiply with the density and the number of columns. The number of columns you can see 1, 2, 3, 4 up to 16. So then we'll arrive 41.4 kilonewtons. Similarly, external wall load along x direction, y direction, internal wall load along x direction and y direction. Here the height is taken as 1.5 meters, similar to the columns. Then the parapet wall, 40 meters is the total length. So that is the parapet wall is along the uh, periphery of the plan, and width is 0.12, that is the width of the parapet wall. 1 is the height, 20 is the density, kilonewton per meter cube, and the number is 1. After simplifying, will arrive 96 kilonewtons. So after summing up of all the weight values, then will arrive 879.61 kilonewtons. So these load calculations are for seismic weight of third floor. Similarly, for second floor and first floor, here we need to consider the floor finish load and live load. Floor finish load we consider as 1 kilonewton per meter square, and live load is considered as 3 kilonewton per meter square. Except these two values, the remaining values we sum up, and for these two values, you need to consider 25% as the live load. So as it is mentioned in IS 80, as it is mentioned in as IS 1893 2023 draft code, we need to consider 25% of the live load. So here the value is less than or equal to 3 kilonewton per meter square, then we need to consider 25% of the live load you need to consider. So the seismic weight calculations for second floor and first floor are as follows, and the total weight the calculated as 1256.48 kilonewtons. Then similarly for ground floor, even ground floor also the calculations are same. So that's why we arrived at 1256.48 kilonewtons. Then the total seismic weight of the structure is the summation of seismic weight of each floor, that is 879.61 plus 2 times of 1256.48 plus 1256.48, then we'll arrive 4650 kilonewtons is total seismic weight of the structure. Then design horizontal base shear force, that is VBDH, the design horizontal base shear force and design vertical base shear force VBDV along any principal direction of the building for strength design shall be estimated as follows. The base shear force is equal to AHD of T multiplied with W along X direction as well as Y direction for strength design and serviceability check. The values are arrived. VBDH along X direction 174.375. Similarly for Y direction for strength design. And serviceability check, the VBDH along X direction and Y direction, the value is 87.1875 kilonewtons. As it is mentioned in IS 1893 2023 draft code, the minimum design horizontal base shear force VBDH minimum uh, for strength design shall not be taken less than the given formula, that is 0.625 multiplied with ZI by R multiplied with W. After simplifying, the value is arrived 43.6 kilonewtons. In no case, the value is less than 0.015 W, which arrives 69.75 kilonewtons. After obtaining the base shear force, that base shear force is distributed onto the every floor level. The design horizontal earthquake base shear force for strength design and for a serviceability check shall be distributed along the height of the building and in plan at each floor level. The equation is as follows: Qi is equal to Wihi square divided by sigma j is equal to 1 to n Wjhj square whole multiply with Vb. Vb is the base shear. So the tabular column clearly shows the calculations. For first floor, the value Qi value is 6.92. For second floor, 27.67. For third floor, 62.27. And for fourth floor, the value is 77.50. So if you add all the values, then we'll arrive 174.375. So the distribution of the design horizontal base shear force at each and every floor level is drawn in the form of a schematic diagram. First floor, second floor, third floor, and fourth floor. And the base shear is 174.375 kilonewtons. This is in X direction. Uh, and the values are similarly for Y direction also. Similarly, for serviceability check also, you need to calculate the Qi value, and the force distribution is shown in the schematic diagram. Distribution of story shear onto individual frame elements. In buildings whose floors are capable of providing rigid horizontal diaphragm action in their own plane, VI can be distributed to the various vertical structural elements in proportion to their lateral stiffness. And in buildings whose floors are not capable of providing rigid horizontal diaphragm action in their own plane, VI shall be distributed to the various vertical structural elements in proportional to the masses from tributary floor areas. Next, the design horizontal base shear force is calculated as per IS 1893 2016. Here you can see the design horizontal seismic coefficient AH both in X and Y directions are calculated as AH is equal to Z by 2, I by R and SA by G, which is equal to in the IS 1893 2016 code for zone 2, the zone factor is considered as 0.1 divided by 2 multiply with I, that is the importance factor is considered as a 1, and response reduction factor R is 5 and SA by G is 2.5. After simplifying, the design seismic coefficient AH is equal to 0.025, and from that the seismic base shear value is calculated. Vb is equal to Ah multiplied with W, which is equal to 116.25 kilonewtons, and the base shear value is same for both X direction and Y direction. As per IS 1893 2016, the VB value in X direction 116.25 and in Y direction also 116.25 kilonewtons. But whereas as per IS 1893 2023 draft code, the X and Y values for strength design, the value is 174.375 kilonewtons, and for serviceability check, the values are 87.1875 kilonewtons. Here you can see the difference between the strength design of IS 1893-2023 draft code and IS 1893-2016 code. The seismic base shear as per IS 1893-2023 draft code is more than 66% than IS 1893-2016 code. Thank you. Jai Hind.